Good day, dear participants of the conference. With your permission, I present a work, Optimization of Helicopters' Aircraft Engine Working Process using Neural Network Technologies. The development and operation of complex technical systems at the modern level involves the mandatory use of their mathematical models, which can be defined as a mathematical image of the essential aspects of real system or its design in a convenient form that reflects information about the system. With regard to helicopter turboshaft engines and its modification, which is a complex technical system, during its creation and operation a large number of mathematical models of different type of the engine as a whole and its individual components are developed. Calculation based on a finite elements method FEM used in modern practice require a significant amount of computer time. The method of multicriteria optimization based on approximate models for dynamic systems was developed by Yurii Zelenkov. However, the implementation of this method is possible only at the design stage on an aircraft engine. Therefore, the actual scientific and practical tasks solved in this work is improvement of this method in relation to helicopter turboshaft engines at the mode of their flight operation, that is, in real time. Analysis of even simplified method of thermogas dynamic calculation of aircraft gas turbine engines, including helicopters turboshaft engines, shows that more than 13 parameters, independent variables, affect the definition of the working process and consequently the design of the engine. In this case, the dependencies linking the target and independent variables are nonlinear, and it is impossible to guarantee that they are different table function. Today, a number of multicriteria optimization methods are now based on nonlinear programming and genetic algorithm. One of the most efficient constrained multicriteria optimization algorithm in the NSGA-II genetic algorithm. The investigated dependencies are interdisciplinary. It is impossible to guarantee the differentiability or convexity of these functions. In addition, when developing new products, the task is never to find the best parameters of a new product, the global Pareto optimal set, and all efforts are directed only to ensuring the specific technical requirements. Very often a solution is chosen with less efficient parameters but providing greater resistance to deviation that inevitably arise during the production process. In the course of the work, a detailed analysis of the architectures of neural networks was carried out, which were used in solving the problem of multicriteria optimization. The choice well of the radial basis neural network, RBF. For RBF-network training, a gradient algorithm based on minimizing the objective function of the network error is used. In accordance with this algorithm, for each element, the values of change in the weight coefficient, element width, and element center coordinates are calculated. Evolutionary algorithm for construction a neural network of a radial basis is shown in figure. To evaluate the efficiency of the proposed algorithm, consider the problem of approximation of the function. The diagram of the function being approximated is shown in figure A. The error of its approximation based on this method is shown in figure B. Thus, the proposed method for generating RBF networks can significantly reduce the computation time and provide more efficient networks with fewer neurons and less error compared to the traditional method. To test the effectiveness of the proposed optimization method, we will conduct research on a linear mathematical model of the TV3117 turboshaft engine. The calculation of the parameters of the working process of TV3117 turboshaft engine must be carried out in several sections: at the engine input, at the compressor input, behind the compressor, behind the combustion chamber, behind the compressor turbine, behind the free turbine, shown in figure. The process of solving the formulated problem in accordance with the algorithm. At the first step, a training set of 50 decision vectors X was generated in accordance with the central composite design of the experiment with centers of the faces. Central composite design with face centered. Of these 15 solutions, 10 met the constraints and 7 were non-dominant. Based on this sample, approximate models were built for target variables and constraints based on neural network of a radial basis, in accordance with the method described above. Table for each model shows the number of neurons in the hidden layer and fitness calculated by the expression. Figure A also shows the Pareto optimal set Pareto front obtained by the NSGA-II method. 100 individuals in the population, 500 generation based on the exact model. Finding this set required 5,000 calls to the minimization function. And figure B shows a comparison of 3 Pareto optimal sets of solution obtained on the basis of the approximate model proposed here. 320 calls to the exact model and obtained on the basis of the exact model for 500 calls, 100 individuals in the population, 5 generation, and for 5,000 calls, 100 individuals in population, 500 generation. Some of the found Pareto optimal parameters of the working process of the TV3117 turboshaft engine are presented in table. The results obtained indicate that the proposed method for constructing approximate models allows reducing the amount of computed time spent on calculation in case of multicriteria optimization with constraints by more than 100 times. The program is protected because the described method is implemented written in Python for the modern library and script. The program is packed with clear modules in order to implement experiment planning, rich criteria optimization using the NSGA-II method, model approximation on the basis of the RBF-network, as it was for analysis more, and a graphical interface of the core. The conclusions are presented on this slide. Thanks for attention.